Thanks very much. Thanks the organizers for inviting me giving this talk. So the title has slightly changed from the time I submitted because I was a bit over-optimistic at the start. So I'm going to speak about integrite deformation, dehydration, and embrittlement, mostly about deformation, actually. So I thank you, Bruno, for this kind of a nice talk that also introduces what I'm going to talk about now. So the outline is the following. I'm going to talk about why I'm doing this, and I'm going to separate my talk into three parts, describing the brittle fields of integrite, so how does integrite deforms when it's like low pressure, low temperature conditions. I'm going to say something about the ductile field. There's quotes about ductile because we don't really know what ductile field means in integrite, and then something about dehydration and embrittlement. So serpentinites are the product of alteration of ultramafic rocks in oceanic crust. So they are hydrosphere silicates. And so I show here for an example of such an alteration reaction. You take forsterite, you add water, and at about 300 degrees Celsius, you generate brucite and lizardite. Lizardite is a low-pressure form of integrite. And so rocks that are altered like this, so look like this picture, which I take from the paper by Malvoisin. So we have these very nice rocks from, I think they're from, I don't know exactly where they're from, but anyway, this is about 61% serpentinized olivine rock. So you have these olivine cores surrounded by this kind of mesh texture. In that case, that's lizardite, completely altered the rock. So this is what it looks like when you look at the bottom oceanic floor, for instance, in exhumed rocks. And so where does this alteration occur? So again, around the ridges where we have these mode 1 cracks, so if you want extensional faulting, where we have hydrothermal circulation. And then as the oceanic plate gets subducted, we have more alteration, you have the sediments that get altered, or also because of the dehydration of those rocks, we can have also hydration of the overlying mantle wedge, which produces also these alteration reactions in the mantle wedge, which may be detectable. So I've just spoke about lizardite first because it's the low pressure form, but most of the subducting slab is actually at high pressure, and this is where integrite is the stable form of these minerals. So it's quite a large stability field. So it extends to 600 degrees Celsius in temperature, give or take, and then it goes to 5 GPa or so. So this is most of the serpentinites we talk about in deep subduction zones is actually integrite. And this is the pressure temperature paths of most of subduction zones. And you see that these PT paths, they cross the dehydration reaction of integrite at fairly high pressure. And actually all of them, they cross it roughly above 2 GPa, where the slope of this curve, this is like the Clapeyron slope of this reaction, integrite gives enstatite and forsterite and fluids, is negative. So there are several questions about integrite. So what do we care about? So first thing is the crystal structure. So it's very different from lizardite. Lizardite is on the left. So these are high-resolution TEM images, which I took from a paper by Evans, 2013. And you see that lizardite is a very, very simple structure. It's like a clay. It is actually a clay, and all these O1 planes are separated by hydrogen bonds. It's very weak for that reason. Integrite, on the other hand, is on the right, is a lot more complicated. So you have this kind of, which you can call them lizardite units, but they're flipped back and forth. The unit cell of integrite is ridiculously big. It's about 70 angstroms, and it has a very corrugated structure. And because of this very different structure, you can expect that at the crystal scale, the deformation mechanism are likely going to be very different between this guy and the lizardite here. So integrite are located in a key location in subduction zone. They are typically at the top of the slab because that's where they are formed in the first place. And so because of this, we think that they control the strength of the subduction interface. So there's been a major debate about how it deforms. The deformation mechanisms, I would say generously, they are poorly constrained, if constrained at all. And all the extrapolations that exist are subject to lots of precautions because of the PT conditions under which they were performed, and also the strain rates under which they are performed. And doing microscale analysis is also very complicated due to the very small grain size and possibly heterogeneous starting material. The big issue as well is that integrite is often referred to as semi-brittle. So it's, to my knowledge, in laboratory experiments, nobody has ever could deform integrite in a purely plastic regime where there's no micro-cracking. It always cracks in laboratory conditions. So there's always a mixture of like dislocations, possibly diffusion, but also micro-cracking. So we need to understand both the brittle and ductile regime if we want to understand how antigrade deforms. And the second interesting point, if I go back to these slides where I show the PT path of the subduction zone, is that antigrade destabilizes in the regime where it's fairly high pressure, above 2 GPa, for which the Clapeyron slope is negative, and that means for that reaction that the total volume change is going to be negative. So the solid volume change is always negative in here, but then under 2 GPa, the fluid volume is larger than the porosity that's created, and above 2 GPa, the fluid volume is going to be very small, and so the total net volume change is negative. So when it dehydrates, it changes into, for instance, here, forsterite and enstatite and a fluid, and low pressure is going to be forsterite and talc and a fluid. And we know from experiments done since the 60s that serpentinite becomes really weak when it becomes dehydrated. This has been termed historically dehydration embrittlement. So this is a plot taken from a famous paper by Rayleigh and Patterson in '65, where they measure the strength. So this is differential stress, but that's a measure of strength as a function of temperature for different types of serpentinite and different heating rates and different pressures. But what you find here is that whatever the conditions, there's a huge drop in strength when you cross the dehydration temperature of serpentinite. And so the explanation, in the physical explanation for why this occurs, historically, has been that because you release the fluid pressure increases, and then because it increases, it decreases the effective stress. And because of this, you come back to the brittle regime, so you hit a failure of flow criterion. In that case, I just drew a schematic of a Coulomb-type criterion, and then you can have rupture or flow of the rock at this very, very low stress. The problem is that, again, the volume change of these reactions for all this subduction zone is negative. So if you don't deform anything, then the pore pressure should decrease when you do the reaction. So you can't really explain this as simply as this at high pressure. However, in experiments, there's this famous paper by Young, Green, and Zabryzhenskaya, in which they deformed and dehydrated antigrade at very high pressures, and they still saw acoustic emissions and faulting, and they interpreted it as dehydration embrittlement in the very high pressure regime. So the question is, what is the physical mechanism for this, and how can we get fluid pressure in the high pressure regime where the volume change of the reaction should be negative and the fluid pressure should decrease? So the questions are the following. What are the deformation mechanisms of antigrade, so intact antigrade before, at low and high pressure, and what controls the process of embrittlement at high pressure? So the methods we've done is to do laboratory rock deformation experiments, characterization of the material, and some mechanical modeling for the dehydration embrittlement parts of this work. So I've not done this myself. Actually, 99% of this work has been done by my postdoc, Emmanuel Davids, at UCL, in collaboration with Lars Hansen at Oxford, Greg Earth at Brown, Oliver Plumper in Utrecht, Ian Jackson at ANU, Tom Mitchell at UCL, and the modeling has been done with Yanis Stefanou and Jean Sulem at ENPC in Paris. So, the brittle field. So I'm going to deform antigrade in a brittle regime, try to understand how it works, and if it's similar to other rocks we know about. So the sample material was all nearly pure antigrade for Vermont, US, 98% pure. There's a small amount of magnesite in some veins, so this is the four scattered electron map of the starting material. The scale bar is 100 microns. So this material, surprisingly, is elastically isotropic. It's polycrystalline. And we don't see any clear CPO in this intact initial material, which is why we use this. So we have the simplest antigrade rock, if you want, as a starting material. What's very nice in this SEM picture is it highlights the very, very broad gradient distribution in this rock. You start from something that's about 1 micron, 10 microns here, and you have these big elongated slabs of antigrade that go above 100 microns in dimensions. So this rock is, at microscale, very heterogeneous, but at macroscale, very, very homogeneous and isotropic, I insist. So we do triaxial experiments. So very simply, we take a rock core, and then we apply a confining pressure on the surroundings and a differential stress, so we deform it actually. And we place it in a jacket that's equipped with a PNS ultrasonic transducer, so we can measure the wave speeds, PNS wave speed during deformation. We record also the local stress and strains using strain gauges. And these rocks have been deformed at confining pressures fairly low, I would say 0.2 GPa and room temperature. So it's in a brittle regime, let's say. So mechanical data for this simple test. So on the left-hand side, I'm going to plot a differential stress versus strain curve. So differential stress is equivalent to a shear stress, and actual strain is equivalent to a shear strain. So this is a stress strain curve. And so we see something that's very classic for the brittle regime. We start with having slight nonlinearity at the beginning. It becomes linear, and then it deviates from linearity. It yields at fairly low stresses in here, and then it deviates, and then we have a peak stress. And at this peak stress, then the rock fails. On the right-hand side, this is the mean pressure volumetric strain. So essentially, that's the isotropic part of the stress and strain curve. So you see, you start at 150 MPa because that's the confining pressure we start at. And then the volumetric strain keeps decreasing and decreasing and decreasing. So we elastically compact the rock. We measure this locally. And at some stage, we have some amount of dilation and it breaks. So the key element of these two curves that I want to highlight here is that there's almost no dilation before failure. I'm going to show the comparison with granite later. You're going to see how different that looks. So this is a key element of antigrite. It's very different from all rocks I know, which doesn't dilate very much. So the second element is that we have a strong pressure dependence. So we repeated those experiments at 20, 50, 100 MPa. Again, you see similar curves, linear, and then it breaks. And you also see this very, very nice pressure volumetric strain curves. And it only dilates very, very late in the game, if you like. It dilates only when it starts breaking. And as a comparison, we also repeated a test on westerly granite, because it's a very standard material for the brittle crust. And granite looks like this. So at 100 MPa, the strength of granite is about 700 MPa, so it's not too far from antigrite. Antigrite breaks at about 550 or 600. But you see the dilation here. So before failure, granite dilates a lot more than antigrite. And actually, the part of these curves that are dotted is when the strain gauges, which measure the local strains, diverge between each other, which indicates strain localization. So we're not even sure if that part is actually real dilation. It might just be the onset of strain localization. But again, that's very qualitatively different from granite, which dilates a lot more. So then we did also a series of tests trying to probe the effect of cyclic loading on this material. So I'm just going to show one summary plot here for one effective pressure, which was a confining pressure, 150 MPa. So again, we vertically load the material in cycles. So as we go up and down, we see that we have some yield, and then it unloads. We recover some of that strain. Some of that strain is irrecoverable in shear. So again, actual strain is a measure of shear. Then you start again, you go above, and you unload, and so on and so forth. And what you see is that we have lots of dissipation in shear in this material. So these loops here corresponds to dissipated energy that's been lost by internal deformation mechanisms and friction in a generic sense inside the rock. However, if you plot this diagram in a mean stress volumetric strain curve, again, that's the isotropic volumetric part of the deformation, there's absolutely nothing. So this is completely zero volume change except for the elastic part. So there's no inelastic volumetric strain. There's no dissipation in a bulk part, but there's a huge amount of dissipation in shear. Again, that's very different from everything we know in rocks. We also measured the P wave speeds, and we also measured S wave speed. I'm just going to show the P wave speed for now because that's the easiest way to look at the problem. So here I plot the relative change in P wave speed as a function of effective mean stress. So the first part of that curve, the dashed line here, corresponds to the isotropic compression before we start deforming. So again, this is the squares here in the dashed line. You see that we have a 10% increase in P wave speed when we increase the confining pressure from 0 to 150 MPa in this rock. The fact that we have a 10% increase means that we must have a loads of pre-existing cracks in this rock, so which can then close and then increase the effective wave speed of the material. Now, after this initial increase due to confining pressure, when we deform, we see almost nothing. There's a slight drop at the end, which is of a few percent. But that's again, completely negligible to what we see in other types of rocks. So we see this effect at all pressures. You see that we have a nice increase during the isotropic loading, and then very, very small minor variations during loading. So again, for instance, at 50 MPa, the wave speed or the horizontal wave speed here moves by about less than 1%, which is almost nothing. By comparison, if you take granite again, which is a nice candidate for the brittle crust, granite does this. So we have a nice initial compression. Again, lots of pre-existing cracks in granite, so we're not surprised there. But then as we start loading, the cracks open very, very easily, it dilates a lot more, and then the wave speed drops by about 10 to 15%. And that's very different from antigrite. You see that the drop here is about 1%, this is 15. So the microstructures, when we look at the deformed rock, well, there's not much to say about this, except that there's a big fault. Well, a big fault, this through-going fault in the sample. If we zoom on that fault, we see lots of microcracks. The fault is here, sorry. And then outside the fault, essentially, there's nothing. We try to look for indications of strain or strain markers outside the main fault. We absolutely see nothing. So it's extremely localized. It's an extremely brittle material, and it's actually very, very strong. If you go back to this plot, it is almost as strong as granite, even though there's no dilation, there's no cracks outside the main fracture in this rock. So the conclusion for that part is that we start with the material that's isotropic, but has loads of pre-existing cracks, and we can close them. But these cracks do not propagate when the rock deforms, unless at failure on the fault plane. We have a large shear dissipation, but no volumetric dissipation. We have almost no little P-wave speed variations. It's also true for P at different angles. It's also true for S-wave speeds. And we have also a strong pressure dependence of strength. So these are quite puzzling observations. It's a very unique rock. And so we interpret this as, first, we have no mode 1 crack opening, despite cracks being already present. And it seems to us that deformation is dominated by shear cracks. So this is also something that's been hypothesized and observed by Javier Escartin in his 1997 paper. So we just have propagation of shear cracks in their own plane and not mode 1 cracks. So the mode 1 is probably limited due to the strong crystal anisotropy combined with a small grain size and this prolate grain shapes, so needle-like grain shapes. If you had an isotropic, more isotropic mineral, then we could easily open mode 1 cracks from the pre-existing shear flows, but it doesn't happen near, mostly because I think cracks can only open in the O1 plane of antigrite and nowhere else, and essentially it constrains the material to be very, to avoid having any mode 1 crack opening. And then if we go to the ductile fields, again I say quote ductile because you're going to see it's less easy as this. So a lot of previous work has been done in this regime, so I'm not going to cite all the papers, but I think there's a very nice summary diagram in the paper by Chernak and Hirth in 2010. So it's a bit of a busy diagram. So here I'm going to show the differential stress. So that's a measure of shear strength of the material as a function of confining pressure. So you see this range from 0 to 1.6 gigapascal, which is like, let's say, 60 kilometers depth, 40, 60 kilometers depth. Two types of symbols here. The open symbols, so these open triangles, open squares here, corresponds to deformation conditions for which the sample the deformation in the sample was distributed. There was no obvious one single fault plane in these samples. All the field symbols, so these triangles here, these here, these here, and these here, are for experiments for which the deformation was highly localized on one single fault plane. So you see there's a bit of temperature dependence, so we go from the gray symbols to the red symbols, from room temperature to 500-600 degrees C. There's a decrease in strength, but very strikingly, we go from distributed deformation to localized deformation at high temperature. So again, this has been investigated again by Greg's group with his student Brooks Proctor, and they observed a ductile to brittle transition in thermally stable antigerites at mantle pressures. It's very, very peculiar. It's the only material we know that does this so far. So we repeated a few of these experiments at Brown University and the Griggs apparatus. So this is a picture of a equipped Griggs sample. So we have alumina pistons. These are 1/4 of an inch in diameter, sample in a silver jacket. And we take much smaller samples because again, we need high pressure. And we have only external load displacement measurements, but we can go to 1.5 GPa, temperature to 500 C. So again, we are much closer to the real conditions of subduction zones. And we did direct cyclic loading pre-scene and post-peak stress strain curves. So the idea was to get the detailed macrostructural evolution of antigerite as it deforms in this regime. So it's still ongoing work, so I'm going to show very preliminary measurements of these microstructures so far. So stress strain curve again. So yeah, this is the experiments performed at 1 GPa 400 degrees C. These are quite, I would say, easy to do. So you can do several a week, for instance. And we stopped the experiment at before peak at 0.5% plastic strain, or at the peak, 1-2% strain, or one was stopped after 11% strain. So we have the full evolution from pre-peak to way after the plastic flow has started. So a striking feature, I mean, look at the scale here. This is 1.5 GPa differential stress. You need a huge amount of stress to deform this rock, even though it's at 1 GPa 400 degrees C. So antigerite is very strong. And it's also very brittle. If you look at this curve, there's a peak stress here and a strain weakening. So these features are typical of the brittle regime. Remind you, this is 1 GPa 400T. This is brittle. And there's one single fault plane in this rock. So if we take the microstructure of a sample that's deformed at the peak here, so I had a slide on the microstructure before peak, but you see nothing, so I skipped that slide. There's actually nothing in the sample deformed here. So if you now look at the sample deformed here at the peak, which is 1 or 2% strain, we have those decompression cracks. Don't look at them. There's one shear zone here. So this is some of these features are due to the polishing, but this is the main shear zone in the rock. If we zoom on this here, and then we took cross sections. So we take a flip cutting. So we go to the focused iron beam in Utrecht, and we cut a cross section across the fault. This is what you see. So the scale is very, very small. It's 5 microns across. So now we look at essentially the geometry of this is that you look at cross section of the San Andreas fault. So the motion is out of the plane. The stresses are on horizontal here. And you see that the fault is extremely narrow. This is less than a few microns thick, and you have a small gouge here. So there's no indication of plastic deformation outside this. The only feature we see is this main fault, which is very, very thin. We did TEM observations within that zone. So again, same type of geometry. This is now 2 microns wide. And you see you have these blades of antigerite. They are all cracked. Oh, sorry. This is actually opening cracks due to decompression probably, so I wouldn't think about this too much. But you see you have some indication of plastic flow. These fringes here indicate a bending of the slab of antigerite. We don't know if it's elastic bending or plastic bending, but it can be either. But there's very little strain except for these cracks, the very elongated cracks separating the blades of antigerite. If we now look at the microstructure post-peak, again, this is a picture, the microscopic picture of the full sample. This is 2 millimeters. The main shear zone is here. Outside, there's no indication of deformation if we zoom in. And I'm going to just show one of 2 pictures of what it looks like here. So this is, again, same orientation. So you see this notch here corresponds to that notch here. So we have the shear zone. And you don't see this. So this is four-scatter electron. We don't see any indication of deformation except for the fact that it's elongated, these elongated shear zone here. And then if we zoom on that, we don't have preliminary information, but this is what it looks like inside this kind of mush here, a very, very small grain size. So you see, you see that you have some cracks. You have a grain size reduction that's completely ridiculous. So we can't see any grains here at this scale. And we tried to zoom in even further, but we couldn't get the high resolution with this SEM and Oxford. And so essentially, what we have is extreme grain size reduction and no indication of dislocation creep or dislocation dynamics or diffusion at that scale in those experiments, even though we are at 1 GPa 400C. So the key observations from this study, again, it's preliminary. We have to do a bit more of work to quantify this and see whether we have amorphous materials, which is very likely we do. But again, we see a weakening and localization at high pressure, high temperature. So this rock is still brittle. We have extreme grain size reduction, and we have no evidence for pervasive intracrystalline plasticity outside the main shear zone. So we interpret this as the mechanism being still brittle at the grain scale. So we have cleavage, delamination, and maybe some kinking of the crystals. And we, of course, we never have enough deformation mechanisms to have complete zero-volume plastic flow in this rock, so it remains semi-brittle. We have to fracture the material to accommodate all the deformation. Again, I remind you that 1 GPa 400C is quite high, but for silicate, diffusion of silicon or species in intracrystalline diffusion at 400 degrees C is almost zero at this temperature. It's way too small. So again, we need dislocations, and we don't have enough dislocation systems in antigerite because of the corrugation of the planes. We can't slide on the basal planes that easily because we have to overcome this kind of corrugation at atomic scale in the crystalline structure of antigerite. So antigerite remains a very elusive material to study. It's very, very hard. But still, I think the main point I want to make here is that it's very strong. It's strong and stable. And it's semi-brittle at high pressure, high temperature. So now what happens if we dehydrate antigerite? So I'm going to move on from experimental work to more theoretical work. Modeling I did with my colleagues at ENPC. So I come back to these slides where I show the PT diagram for antigerite. And again, I insist that all these subduction zones cross the antigerite phase boundary in a negative Clapeyron slope here, which means that the total volume change is negative. So if I want to sketch what it looks like, we start from an intact block of entegrite, there's 0 or next to 0 porosity, and then as we cross this phase boundary, we transform the solid matrix from entegrite to enstatite and forsterite, and we have to accommodate some water inside as inclusion, so we can consider them as pores. And because in these conditions the water is very compressible above 2 GPa, we generate a pore volume that's larger than the fluid volume that fits in it. So if nothing else happens, so if I just take that very basic sketch, the fluid pressure should decrease. I mean, it's the definition of equilibrium, right? Because if the pressure increased, then it would be a runaway problem. So the question is, if in that condition, how can we explain that we may have instabilities, and what is the consequence of this transformation and the mechanical behavior of the aggregate? So we found that, I'm not going to go into the details of the model, it's quite tedious, but it's based on very simple principles that essentially the material behaves like a porous rock, because it is a porous rock at this stage, at least transiently. It's time-dependent in plasticity, and then we have the feedback between pressure and reaction rate. Essentially, we just say that the reaction kinetics of that, the kinetics of that reaction is proportional to the delta G of the reaction. And in that case, because the pore pressure enters in the delta G, we have a coupling between the pressure generated by squeezing the rock, the mechanical pressure, essentially squeezing the sponge, and the pressure that enters into reaction kinetics. So what we find is that if the aggregate strength degrades enough with increasing porosity, and we have, in that paper, we have a hard criterion, like a mathematical criterion for what we mean by degrades enough. But in terms of the sketch, it's like this: if it degrades enough with increasing porosity, then the fluid pressure grows exponentially. So it's a diffusive instability. So it looks like this. We start the reaction, we generate the porosity, and we compact it, because again, remind you, we are at quite great depths. We have 60 kilometers or 100 kilometers. We have lots of lithostatic pressure to compact this. And essentially, if it weakens enough, then we can compact so that the fluid pressure increases, like, again, making the sponge and squeezing it as we're making it. And because the fluid pressure increases, the reaction progresses faster, we create more porosity, and we compact even more, and so on and so forth. So if you want, we're doing this. We are at this boundary, and because we have a negative Clapeyron slope, as we start dehydrating, we move upwards here. So we go away from the reaction boundary, and it's a positive feedback, which generates deformation and more reaction. So the reaction is quite quick. And it's an instability, so it's an exponential increase in rates. So it has also consequences for the strength of these materials. So now I'm going to plot a failure envelope. So again, it's going to be a shear stress versus effective mean stress plot. I was working with civil engineers, so they like to plot positive stresses in tension. So this is on the negative side. But again, the concept is the same. We start from an initial state with some initial shear stress and some essentially sublithostatic fluid pressure. And then as we start the reaction, we all collapse. We compact these aggregates, we accelerate the reaction, and we decrease the shear stress by the same process. So, which means that any sublithostatic fluid pressure and elevated shear stress will quickly vanish as soon as the reaction starts, because we have an instability. And instability is exponential in rates, and the strain rate scales with the reaction rate. So it implies that dehydration can produce failure in the material, due to compaction. Essentially, even though thermodynamically the volume change is negative, we can generate the pore pressure anyway because of the compaction, and it can be fast enough to make an instability. Now, this is not an earthquake. This is just compacting an inclusion. It has nothing to do with making an earthquake, and the time scales for these instabilities are way too long. These are years. These are not seconds. So what happens is that this is unlikely to produce an earthquake on its own. What's going to very likely happen is that the zones of the subduction zone that will dehydrate will act as weak inclusions. They're going to compact very easily, and two effects can be highlighted here. First, we have this fluid pressure that has to come out at some stage, and so the fluid pressure will diffuse out of these inclusions, and that also helps reducing the effective stress around them. And also, we have the stress transfer, because we have these very weak inclusions of compacted dehydrated rock, and they act as weak inclusions. And there's a very nice example of that discussion in a paper by Rutter in 2009, saying that essentially, even though the dehydrating entegrite might not produce an earthquake on its own, it might transfer the stress outside stronger surrounding rocks that may then generate an earthquake. So to conclude, entegrite is a very unusual material. It seems brittle and strong at all tested conditions, including high pressure and high temperature. Deformation is dominated by shear cracks, delamination of cleavage planes. That's consistent with pre-existing data from Escartin. And we keep the pressure sensitivity even at high temperature, within the stability field, of course. And it's even more brittle at high temperature, which is even more puzzling. So we think that there's an effect of internal friction, but it's not completely clear at this stage. We still have extreme strain localization and grain size reduction, but we don't see any development of fully plastic flow, again, under the conditions tested, which are fairly high strain rates and no fluids. Interpretation is that cleavage plane might not be the glide plane because of the corrugation. We may have frictional processes still active at high pressure at temperature, and the reason why it becomes more brittle at high temperature might be because the internal friction decreases with increasing temperature. Again, if we think of delamination of cleavage planes, the cleavage planes are held by a few covalent bonds, but also lots of hydrogen bonds. And so diffusion of hydrogen can be quite fast at these fairly low temperatures. So it might help the delamination process. And at on a phenomenological level, you can understand this as a lowering of the effective internal friction on the glide planes, on the basal planes. The key point also is that during dehydration, we can consider that it behaves like a porous rock, and we can use concepts from soil mechanics and porous rock mechanics to understand how it deforms mechanically. And so the problem we have is we still don't have a rheology for this, because it's not clear at all that we'll ever have a steady-state microstructure, at least in laboratory conditions, for this rock. So the steady-state flow law for this, I think, is not in sight for now. We need to do more. Also, the problem is, I haven't touched upon this, but it's a huge problem, and I think it's very challenging to do in the lab, is to look at the effects of fluids. It might be that pressure solution is a critical deformation mechanism for these rocks, but it's very hard to test so far under the subduction zone conditions in the lab. So the consequences for subduction dynamics is that the brittle processes might still dominate the subduction interface, but they might not be detectable by seismic methods. Again, there's no dilation, and there's actually no anomalous attenuation of these rocks, so we've done experiments separately. I don't have time to show it here, with Ian Jackson on low-frequency attenuation of antigraphite, and it's not anomalous at all. It's a bit weak, but it's nothing special about it. It doesn't dilate, so again, there's no indication of microcracks that could be detectable by VPVS, for instance. And again, the dehydration embrittlement at very, very high pressure might be triggered by unstable compaction of these rocks. Thanks very much.